maybe one person missing. I don't remember if it was 28 or 29 before. So before we get much further, let me just make sure that I don't have a problem. And I am going to, again, share this screen and see if this works. Do you see anything?
Yes.
Okay, good. Okay.
We've got Chris.
That's gonna suck. Okay. So
And Chris will be joining us for the class sometime in the next few months.
yes, that's right. And he's going to be talking about the other aspect of what we did. And so it'll be a good complementary thing. Okay, so I'm going to try this again. And yeah, I'm going to keep an eye on, I'm not going to make it full screen on my end so I can keep an eye on the window to, if anyone has a problem, I can catch that. Okay, I'm starting again. Here we go.
Okay, everybody on the deck ready? Okay, VTOLs are ready for signature. Okay, here we go. Launching in
Do you see?
3, 2, 1. Launch now.
It's showing the logo, but
Here on the research vessel Falcor here. We were here in the fall of 2016 off the coast of Darwin, Australia. We're back again on the Falcor, this time north of Fiji, studying Trichodesmium.
Trichodesmium is a really interesting beast organism.
Ajit, we're getting messages that it seems to be frozen.
These blooms can.
Sorry, Mike.
We're getting messages that it seems to be frozen on the SOI logo.
So you're not seeing the movie after that?
No.
I'm not quite sure what the problem is. Okay.
Try hitting the double bar and see if you get the arrow.
All right. So plan B, that's unfortunate. The plan B is going to be that I will send you the links. So what I've done here is there's a series of videos that are available through the SOI website. And I will pop the link to the SOI website in the chat window for you to go explore by yourself afterwards. In any case, that's a good idea because there are far more videos than the 5-minute snippet that I made here, which was really just to highlight some aspects of the cruise. You might actually enjoy quite a bit of the other videos that are available through the SOI website. So I will go ahead and do that. I'm going to stop sharing the movie link, and let's see. I'm going to get rid of that. That's a bummer. I've done this with classrooms. I mean, I taught a class in Stockholm last month when it seems to have worked out fine. So I'm not quite sure what the deal is, but whatever.
Usually I'm to blame.
No, I don't know. Whatever it is, it's disappointing. So I have put this in the chat window, but don't get distracted. Let me go through my thing, and then you can go and check that out. But
Okay.
I just want to put it out there, and then I think I might have sent this to Mike. But anyways, I can request Mike to send it out, broadcast it by email.
I'll put it on the website.
Yeah.
You're at the class website for this session.
Okay. So let's say I'm back to my PowerPoint, which hopefully you all see. And I should keep my chat window open just so that if someone, I'll try and monitor the chat window if there's a problem. So do you see my PowerPoint? And I'm not going to go,
Yes.
Can you do that? I wonder what happens there. Oh yeah, okay, I can do this. Okay, so we are seen with the movie. So let's get into Trichodesmium. So it's, as Mike said, it's also known as sea sawdust. And the reason is that if you run into a really dense bloom, actually it does look like someone has been sawing wood and sprinkled it in the ocean. It has very much the same size. It's about 1 millimeter or so. It's kind of brown green in color. So maybe fresh wood. The thing is that it can form blooms that are so dense that from a ship, when Captain Cook was doing his voyages, and they ran into blooms of trichodesmium off the coast of Australia, they actually were afraid of, they were going to run aground because it was so thick that it looked like land to them. They were right off the Great Barrier Reef where there were shallow corals, and they were really afraid of that. To the question that was asked, this is one of the organisms that forms a red tide, but not the only one. This can make the waters red. There's also a story that the Red Sea is called the Red Sea because of massive blooms of trichodesmium that happen there. I don't vouch for any of those things, right? But that's basically what people say. It's called the Red Sea for some reason. This seems like as good a reason as any. It's a cyanobacteria. What does that mean? Which means the thing is that it's a bacteria, so it is not a eukaryote, but at the same time, it does photosynthesis. So it basically has the pigments and the organelles in it that can capture sunlight and take up oxygen to produce sugars, like any other phytoplankton. So for the longest time, this used to be called blue-green algae because it was an algae, but then unlike trichodesmium, which is found in the ocean, you have a lot of these same cyanobacteria that are found to make blooms in lakes and freshwater ponds. And those actually have a different set of pigments, and they are blue-green when you dry it out. And so those are called blue-green algae. And since trichodesmium is in the same family, sometimes people, in the old times, people called it blue-green algae, but now we really want to distinguish it and say these are bacteria, not algae, in that sense. Like I said, it's a prokaryote. It doesn't have a nucleus in the cell. It used to be called blue-green algae before it was recognized to be a bacteria. It's an ancient organism. Cyanobacteria have been around for more than 3 billion years and one of the first oxygenic organisms. It fixes carbon. Like I said, it basically does photosynthesis, and which means it can take up carbon dioxide from the atmosphere, convert it into solids that are then used for its growth, as well as making that carbon available for other things to grow on. So when you have zooplankton that come and munch on something, they consume that carbon and set up the food chain that basically goes up to other animals. But what is unique about trichodesmium, or a few organisms that called diazotrophs, is it also fixes nitrogen. Who cares, or what does that mean? Well, nitrogen is an essential nutrient in the ocean. You need nitrogen to grow. Everybody needs nitrogen to grow. But in the open ocean, nitrogen is the limiting nutrient. In other words, you cannot grow because you don't have enough nitrogen. Therefore, a bug that basically has solved that problem and can basically carry its backpack with its own supply of nutrients is going to succeed where few other organisms can. Just so as a sort of a context here, these bugs have been around for a very long time, and they have evolved to basically thrive in the environments they thrive in, because the ones that didn't, we don't know of anymore. They died off somewhere along the way. So the fact that this can fix nitrogen means that it can live in waters that are very poor in nutrients, such as the tropics, where, just think of it, right? Let me just throw this out as a question to anybody who wants to answer, which is like, what's your favorite beach and why is it your favorite beach? Anybody? No, it's not a trick question.
Eagle Beach, Aruba.
Okay, and why is that?
Because it's beautiful, and they say that, well, at least there, they say it's the only place in the world where you have 7 different shades of blue.
Right, thank you. That's the blue that was the answer. That was the part of the answer I was looking for. The water is blue. And as beautiful as it is also indicative of the fact that nothing grows there because there's nothing in the water. If it was a rich, productive place, it'll probably be green with lots of phytoplankton, and then you'll have fish eating the phytoplankton, so on and so forth. So the fact that most of the tropical, if you think of blue water, you basically go to tropical regions, and you'll see in the video when you actually get to it, the waters that we were in were as blue as I've ever seen. Maybe at the end of the talk, I'll show you a couple of photographs, because just to say, these are the bluest waters, which means that there's really nothing in there. Very, very few things grow. Trichodesmium thrives because it can fix its own nitrogen. That's the bottom line. The other reason we have been really excited about studying trichodesmium or any phytoplankton that can fix nitrogen is that we also think of it as responsible for carbon sequestration, which basically has consequences to climate change. If you're able to take out carbon dioxide from the atmosphere and sink it down to the bottom of the ocean, you're taking it out of the greenhouse effect and you're making it disappear for a while. As a context, I'm almost absolutely certain that all of you know this, but as a context, all the oil that we drill for in the ocean comes from algae that basically sank to the bottom, got compressed and turned into hydrocarbons that we are now extracting. So this is the cycle, except that's happening over a very long time frame. We're talking about carbon sequestration that happens in a very much shorter time frame of a year or two, where it's going from the surface down to the seafloor. And for me, it's an enigma. They're just, we call it trichodesmium. Sometimes I call it tricky desmium because it has got a lot of tricks up its sleeve, and we are still trying to figure out many aspects of why it works the way it does. It's commonly found in tropical oceans. Almost every tropical ocean, we'll find incidents of trichodesmium. And here's just a map where the area in green is, you see almost the entire tropical ocean is painted green because we find trichodesmium almost everywhere. Some places that we don't see trichodesmium, like this white patch that you see here in the tropical ocean in the equatorial Pacific, you don't find trichodesmium there because apart from nitrogen, it needs a few other nutrients. It needs phosphorus, it needs iron.
No.
And these are places where you don't have enough iron in the water.
I don't know, that's like mean.
Just walk away.
Where we don't have enough iron in the water, and therefore you don't find trichodesmium in these waters. Also, you'll find there are these gaps here. These are all places where you have a lot of upwelling of cold, nutrient-rich waters along the coast there. And again, you don't find much trichodesmium in those waters because there is enough nutrients in the water that other organisms can thrive, and they outcompete trichodesmium. So it just doesn't grow fast enough for it to compete with the other organisms. This is basically just a slide to say that we were there in 1998, and we historically, so this is New Caledonia, Australia, and the Great Barrier Reef is out here. And we have had people report to us that these are all waters rich in trichodesmium. So we know from other scientists' observations that these are waters rich in trichodesmium. So we went on a cruise that left out of New Zealand, touched in on New Caledonia, then went north into the Solomon Sea, and then went east along, and then we did this big circle around Fiji and Tonga. And we found varying amounts of trichodesmium depending on where we are. At that point, this whole distribution of trichodesmium didn't make that much sense. In other words, this is what we found, but we didn't understand why it was that we were finding what we were finding where we were. This is what it looks like under a microscope. Now, this particular set of slides I'm going to show, or this particular trichodesmium that you see, is much greener. And the color of the organism, to give you context, right? This is a colony. It is made up of potentially, I would say, between 50 and 100 trichomes, which are the single bits in there. I don't think you can see any of them that are really thin here, but you can see that some of them, you can maybe see on the edge that it's a little frayed, and you might be able to see the single bits in there. But anyways, these are made of trichomes, and you have somewhere between 50 and 100 of these that basically stick together and make a colony. Now, each trichome, like your hair, and trichome has something to do with hair in Greek. So I don't know exactly right now what it is, but it has there's a relationship there. But anyways, it's thinner than your hair, and each trichome probably has about 200 cells. So when you see a colony like this, you're probably looking at about 20,000 cells, individual cells that are all together. And this is what it looks like under the microscope. This is a photograph I took while on this cruise. Okay, I do. So you can see here, these are the individual trichomes I'm talking about. So that's what it looks like when you really sort of zoom into it. When you zoom out, and if you basically are in a bloom and you throw a bucket over the side and you pick it up, you see this. You see something that looks like this. And now you can start seeing, what I mean when I say it looks like maybe this is again slightly green, but trichodesmium is often quite red or brown, and then you can imagine why it might look like sawdust. This is not trichodesmium. This is a kissing cousin of trichodesmium. This is another cyanobacteria that fixes nitrogen and blooms very extensively in the Baltic Sea. This is a photograph that was taken through a porthole And I just stuck a meter ruler in there to give you a sense of scale. And each of these are probably in the order of a couple of inches long. And in this particular case, it really looks like there was a blonde person who had a little bit of a haircut. And that's really what it looked like in the water. But you can also see the background of the water is green. So this is a very different environment than the blue tropical oceans where we find trichodesmium. But the organism itself is quite related. This is also from the Baltic, and this is to give you, again, a sense of scale. And now you can start seeing the whole grass clippings, sea sawdust aspect of things, when you have a bloom that you're seeing. This is in the Pacific. This is basically from the cruise. And this is a useful photograph for a few different things. One aspect you might have seen of trichodesmium in the pictures I've shown so the last couple of pictures, is that it's floating at the surface. The reason, and that's unusual for phytoplankton. Phytoplankton usually don't float at the surface. The reason trichodesmium is able to float at the surface is because it has gas vacuoles, little gas bubbles inside of it, and it can control its position in the water column by changing its weight. It literally adds weight to sink by fixing more carbohydrates, and then it respires them, loses weight, and it comes back up to the surface. And it's that by being able to move up and down in the water column, it can also mine for other nutrients that it wants. For example, it needs phosphorus. Phosphorus is found deeper in the water column. It can sink down, get the phosphorus it needs, and then come back up where it can use the light, and where it won't be outcompeted by anything else. So this is basically to show how you get these surface slicks of trichodesmium. What's also useful to see in this picture is that there is pumice. So this picture brings two parts of my story together. And you can see that the pumice actually has an above surface expression, if you follow what I mean. It's basically popping up on top of the water, whereas trichodesmium is slightly below surface. And you know that because you can see sun glint in this, right? So you know that it's not at the surface, because if it were, then you won't be seeing the water reflecting the sun, the sky. Whereas if it is below, just below the surface, you'll see the sky reflection that you see in these bright patches here. However, because this is slightly above the surface, it is more affected by the wind. So it is moving at a different speed than the bloom that it's in. And that's basically why you see a wake behind the pumice. Make sense? So lots to learn from a simple photograph like that. This again is another photograph of a bloom that we encountered in the Pacific. The previous one, the waters were really calm. This is basically when the waters are slightly rougher. And so now you can see it's really broken up and very patchy. And as you can imagine, trying to sample this to get a sense of the biomass is really difficult, because you can sample just literally 10 centimeters apart and either have a lot of tricho in your sample or very little tricho in your sample. So these are challenges that we need to sort of get over. This is back in the Baltic, again, to give you a sense of what it looks like from about a 5-meter height. So this is taken from the top of the mast of a sailing boat that we used in this particular field work that we were doing. And so you can see how these accumulates on the side of the ship that way. This again is taken in the Pacific, and here you can see the blueness of the water that I was talking about. It is absolutely, I mean, okay, let me just do this. Here you can see the water is green, and that's basically the Baltic. And here you see the water is really blue, and that's the South Pacific. But you can also see here how trichodesmium accumulates along the side of the ship, and trying to sample it using the normal techniques we use for sampling seawater really doesn't work. This is a photograph in the Baltic back again, and switching back and forth as a contrast, and also because I have the photographs from the fieldwork I did several years ago. This is taken from an aircraft. And so here you can see the blooms of Nodularia, which is the organism that blooms in the Baltic. And what you also see in this photograph is a ship. And you can see there's a wake behind the ship where you're seeing the Nodularia accumulating along the sides. So this is sort of akin to the photograph I showed you a couple of slides ago, where you had the pumice rock and the wake behind the pumice rock. This is taken from a drone, and I say drone rather than a UAV, because this was one of the smaller DJI drones. There is our little boat. This is not a big ship. This is a little boat that we use for sampling. And you can see how trichodesmium is found in these patches in the water. This is from a satellite back in the Baltic. So that's Sweden back there. You have Germany here, Poland here. And you can see how extensive some of these cyanobacteria blooms can be You basically can have them cover the entire Baltic at sometimes, the Baltic Sea. And this is taken from the space station. And this is a trichodesmium bloom that we see off the Great Barrier Reef. And so that's basically some parts of the Great Barrier Reef. This is in the Capricorn Channel in the Great Barrier Reef, again, showing how extensive these blooms are. This is taken from the space station as well, as a photograph from the space station. And this is of Western Australia, again, showing where you have trichodesmium. The thing to note here is that sometimes clouds look like trichodesmium. So we need to figure out ways where we can distinguish between clouds and trichodesmium when we look at satellite data. This is a satellite image of a similar region. Again, we can see trichodesmium. You can also see here some wakes of ships that are seen from satellites. So now we're looking at regions that we're looking at a region that is something like a couple of 100 kilometers by a couple of 100 kilometers. And so really large regions covered by these blooms. Okay, we don't need to get into the nuances there. So now getting on to the second part of how this works. And I'm now going to go back to the question I asked before, your favorite beach and the color of the water. So the whole point of remote sensing of ocean color is how you can interpret the color of the water to tell you what is in the water. We have satellites that basically have cameras that are looking at the Earth in very narrow bands. I say bands, what we mean is that they're looking at slivers of the wave spectrum, right? So you have a blue band where it basically only measures light in the blue. You have a green band that only measures light in the green. You have a yellow band, a red band, so on and so forth. And what we do is we can reconstruct the color based on the measurements that is made by the satellite. So for example, this particular image is taken from a satellite, from a Landsat. This is taken by a satellite called Landsat. And we have reconstructed it using the red, blue, and green bands to give you something that would look similar to what you would see if you're looking out of the plane window. Except this is taken by a satellite and it's measuring the wavelengths just at a few specific narrow bands. What we do, so you have different kinds of phytoplankton. So here is two different kinds, and they have different colors because of the pigments they contain. This is the absorption spectrum of this particular phytoplankton, and this is the absorption spectrum of this particular phytoplankton. So just as a quick takeaway, this is green, which means it's absorbing the light in the blue. I have a sort of the wavelength scale down here. If you absorb the light in the blue and you absorb the light in the red, you're left with green. And that's basically what you see. Similarly, this is red, where you're sort of absorbing the light in the blue and the green, and you're basically left with the light in the red, where you're not absorbing. So that's why it appears red. It's an easy way to think about how we use this kind of information for us to measure the color of the water and then invert that to figure out what is in the water. And that's how we map phytoplankton. Because they have chlorophyll, we can look for the absorption due to chlorophyll, and then we can estimate how much chlorophyll there is in the water. So one of the maps that Mike showed of Tasmania with the spectacular, beautiful blooms around it is a map of chlorophyll concentrations that is made by the satellite. This is basically, again, to tell you about the different absorption spectra. I don't think I need to get much more into detail about that. But this is only to say that we can stick this into a mathematical model, the absorption and scattering properties, you can stick into a mathematical model and essentially come up with a reflectance spectrum that is akin to what we would see with our eye. So if you had trichodesmium, you'll see something that is sort of green yellowish. That's basically the line that you see here. If you had nothing in the water, you'll see the line that looks like this. It is essentially blue, right? And this is the output of an optical model where I fed it a lot of the details that is needed to do this. And if you have something called coccoliths, I mean, Mike mentioned that he doesn't use the word coccolithophores very often, but here is another occasion for us to use the word coccolithophore. So if you have a bloom of coccolithophores, because they have those white plates, I don't know if you've seen, Mike, have you shown them pictures of coccolithophores?
I think a lot of them know what a coccolith.
Yeah, okay. So they have those white plates, the lids that basically surround them. The way they scatter light gives, when you have a bloom of coccolithophores in the ocean, it'll give it a very milky blue color. And that's, again, when I stick it into the optical model that I developed, you can see that if it basically would have a bloom of coccoliths would basically look kind of bluish, compared to a bloom of trichodesmium, which basically look kind of yellowish. And so we use these kinds of optical models to invert the color and figure out what is there in the water. So now moving on to the next bit, Now we're going to talk about the drones. We used the UAV platform called the Latitude HQ90. And it's too bad I can't show you the videos because it is pretty impressive in terms of how it takes off and lands and the different parts of it. But in any case, the big thing about the Latitude HQ platform is that it can take off vertically. It's a hybrid platform where it can take off vertically and land, just straight going up and down. But then it has a fixed wing and it has a gas propeller at the back that pushes it forward. The takeoff and landing is through electric motors, and the gas motor basically pushes it forward. And that's why it's a hybrid. But the fact that it can take off and land vertically means it can work out of really small platforms like ships. So this is one of the few things we can actually launch and recover on a ship successfully, a platform of this size. Electric motors for takeoff and landing, gas motors for forward motion. The other absolutely amazing thing about this is it's completely autonomous. The pilot basically programs what needs to be done. They start up the engine and then everybody just steps back and the computers take over. And the computers can basically compensate for the heave and roll of the ship. And it basically has sensors that it knows when it comes near the deck, how to basically soften itself and land gently. So the whole takeoff and landing is autonomous. And when it's flying, it literally is with the iPad, you can change its path and it'll change its course. So the whole flying is also autonomous. So there's no one sitting there with joysticks trying to control this. It basically goes at about 45 knots, which is something in the order of about 50 miles an hour. So it can, for most of ocean sampling, that's really fast. It can cover a very large area in a very short amount of time. I'll show you some numbers at the end of this, which will give you a sense of what that signifies. The whole platform weighs about 52 kilograms. So what, 120 pounds, something like that. It has a wingspan of about 5 meters, a little less than 5 meters. So it's pretty big. And the main thing is that it has a payload capacity of about 7 kilograms, which means that we can put some really good scientifically valid sensors in it. It's not just a camera. I'm not sure how much I'm going to get into it, but when Chris Zappa does the Earth to class, he'll talk about all the different meteorological measurements they can make, like air pressure and moisture, humidity, and all the rest of that, wind speed. All of those sensors can be fit into one of these drones. The nose cone is flexible. So, we can land the instrument, take out the nose cone, swap another one in, and have it take off. So we can change out the payloads really fast. And that's a really big deal. And it's capable of flying for 12 hours. So I can put it up in the air and then, at 50 miles an hour, it goes to work for 12 hours, comes back, and it has covered an enormous amount of area. And it also is able to feed us real-time data. So we can use this for hunting for things, as you'll see. We basically fly this out. So one of my vanities, and I'm trying to write this up, is I talk about this as the 21st century crow's nest. In the old sailing ship, you had people basically standing on top of the mast, looking over, trying to see in the horizon what there is. Here we basically have the 21st century crow's nest, where we can basically fly 200 miles out and see what there is and help the ship go find things. We often would do this where we had it flying in circles, in circle patterns, to look around the ship to help us find the trichodesmium blooms, to help us find the pumice rafts, so on and so forth. This is the cruise that we did. And again, I'm really feel badly that I can't show the movie, but you can see it for yourself, because part of what I wanted to talk about when we were seeing the movie was about how we choose where we want to go. When you look at this pattern, it looks kind of crazy, or potentially it could look crazy. You basically see us heading north this way. I mean, this is Suva. We left out of Suva. We went out this way, and we headed north for reasons that I'll try and explain. And then we didn't find what we were looking for, so then we headed south. And clearly we found something we were looking for here. So we did a lot of zigzag patterns here looking for whatever we did. And then we kind of headed west to see if we can find something else. Did a couple of zigzag patterns here. And then we headed east. No, we went east and then we headed west and sort of came around here doing zigzag patterns, and we stayed here for a few days. And when you just look at something like this, you're like, what? How did this happen, right? The thing is that, so this is us heading out of Suva. This is Suva Harbor. How do we find tricho? So what we do is we know something about trichodesmium. we know that it likes warm water. We know that it likes calm water because warm and calm means very little nutrients that allows Tricho to grow well. We know that it needs iron. So there are some constraints as to calm and warm is not enough. It also needs iron in the water. So there are some constraints. So we use satellite data. We were able to pull down sea surface. This is a map of sea surface temperature. It's given here in Kelvin. Basically, this is going from 22 degrees to 32 degrees Celsius approximately. I'm not doing the math, so don't catch me on that. Just subtract out 272 for yourself. But in any case, the thing is that here's what we can do is we can get real-time data of sea surface temperature. So this is like the satellite captured this information either that morning or the night before, and we're able to get that on the ship, download it on the ship, and it tells us where the warm water is. So when we left out of Fiji here, that Suva right here, we basically were heading into the warm water because we figured that's where the trichodesmium will be. And sure enough, when we got there, it was warm. The other thing we wanted to do was calm. So we were also able to get daily wind speed maps from a website called Windy, appropriately. And so we also know on any given day where the calm winds are. So, you know, out here, it's blowing pretty hard, but you can see there's like a patch of calm wind here, there's a patch of calm wind here. So we use this kind of information on a daily basis to figure out where we want to go to sample. And so you can see that, okay, it was kind of blowing a bit there, but then it calmed down after a few days. So we're able to use this kind of, this is the kind of information we need to use to figure out where to go to sample. And sure enough, when we got there, and I don't have to show you photographs after that talk because I actually have it here. This is as blue as I've ever seen, and this is as calm as I've ever seen. So it was gorgeously blue, gorgeously calm, but there was no trickle. And the reason was because we had gone too far north for the iron. Or rather, we figured out that we had gone too far north for the iron. So although some of the conditions were met, not all the conditions were met. So that's why we went all the way north and figured out, okay, this is too far north, we have to go south. But we're still looking for those places where the right temperature and right wind speeds were there. And so that sort of explains why that map looked as crazy as it did. And just as a quick spoiler, yes, we were successful when we went down south and we did those zigzag patterns because that's where we found the trichodesmium. This is a photograph that basically shows you the different payloads that goes into the nose cone of the UAV. That basically just say that you can make a whole bunch of different measurements. Some of these were basically hyperspectral meaning that they are, you have all the full spectrum being measured as opposed to multispectral where you only have narrow bands at a few wavelengths that you're measuring. So we had hyperspectral color sensors, temperature sensors, wind speed sensors on this with which we can go and try and find trichodesmium using the criteria that we have in place. The satellites cannot really measure iron directly. What people have done is a lot of these, there are many sources for iron in the ocean. What we were counting on looking for was iron that is coming from the undersea volcanoes. Spoiler alert, that's what I'm going to talk about later. But in many other parts of the ocean where you don't have undersea volcanoes or they're too deep, that the iron that is released by the undersea volcanoes is never going to make it near the surface. The main source of iron is going to be from dust. So in the tropical Atlantic, for example, the big source of iron is Saharan dust that's blowing off the Saharan desert and then blowing across the Atlantic. And basically, when the dust hits the water, it has iron in it that then finally dissolves and is made available to the phytoplankton. So that's the other, so if you're in really coastal waters, sometimes rivers can provide a little bit of iron, but the satellites measure these things indirectly. We can measure dust by satellites, and then we have to model it to assume how much iron is there. So again, these are photographs to show you the UAV, the latitude with the nose cone out, and that's basically what it looks like. And here you can see the two engineers, Scott and Aaron, sort of fitting the nose cone in. So this is basically, they just plug it in, screw it up, and it's done. So the whole operation takes maybe 20 minutes. This is the control room on the ship, where once the UAVs are flying, we get the data back real time. So you can see in some of these screens, the paths that we put in there so that, you know, I don't know if you can see it very well, but there's like a lawnmower like path where it's basically, you can see some faint lines going back and forth. I don't know if you can see it on your screen, but anyways, this is basically where we tell it, you know, where to go. These are the two pilots, you know, they're basically monitoring the UAV. You can see Chris Zappa, the PI, sitting back there. I'm there. Kelly is there monitoring what's in the water. So when the UAVs are up, we basically are all watching to see what's going on and figuring out where we want to go, so on and so forth. And this is the kind of data that comes back from the UAV, from the cameras. So in this case, it's just a little snippet showing you the color. And so you can see it's blue water, but you can see trichodesmium streaks. And we are able to get this data real time. So we're able to fly this out there and basically get the data and then tell the ship where to go. Because from the ship, we can't see this, or rather, we can't always see this from the ship. But having this extra set of eyes of 200 feet in the air, or 500 feet in the air, actually it's even higher than that, really. It's probably in the order of between 300 feet and over 1,000 feet in the air. We're able to see a much larger region, and it's going also, remember, it's going 50 miles an hour. The ship at the fastest can go 10 miles an hour. So we're also able to cover a huge amount of territory with the UAV. So we're able to map large areas and tell us where to go with the ship, which is much slower. On the right, you're seeing a temperature map. And this is basically one of the objectives of this cruise. What Chris Zappa is interested in is understanding how, when you have surface features like this, it affects the temperature of the water. Because the temperature of water and having something like this will affect the exchange of energy and gases. And so that's basically what that's all about. Then there's this whole thing about pumice. So like I said, we had this unexpected bonus gift where there was an undersea volcanic eruption that happened about 2 months before we got there. And so there was pumice in the water. I knew there was pumice in the water. I just did not know what we were going to see. And as you'll see, why that's complicated. But this is basically what it looks like from the side. So this is a photograph where we took of pumice, just looking over the side. This is one aspect of pumice. So what is pumice? Where does it come from? Just a lot of things. So the word pumice comes from the Latin word pumex, which means foam. And it's because it's foam rock, right? It's light colored. It is extremely porous, igneous rock that forms during explosive volcanic eruptions. And the fact that it's filled with gas allows it to float. So even though you have a volcanic eruptions, down 1,000 meters, 2,000 meters, because these are floating rocks, they come up all the way to the surface. And that's essentially where we see them. So basically it's ejected underwater, it cools, depressurizes, fills up with gas, and it comes up to the surface. And it's mostly made of aluminum silicate, which basically means that while it's mostly made of that, it also has a little bit of iron. And that was basically what I was going after. Is this a source of iron that is helping trichodesmium grow where it does? But it is porous, and then it basically floats till the holes in the rock get filled with water, and then it sinks. But when it's floating in the water, it becomes a substrate for things to grow on. And that's essentially what Lexi is looking at. What are the organisms that grow on pumice? And is there anything that we can learn from what grows on pumice about its properties as a biological agent? This is what it looks like when the eruption just happened. So there was a sailing boat that was somewhere in the region, and you can see that the pumice was almost solid. It's like the sailing boat was on land. And so these are photographs that they made available via the web. And it happened in early August. We were out there in November. The eruption happened here. The sailing boat was about here when they took the photograph. This is the Tonga Trench, the Tonga Islands, and Fiji is out there. And basically, they reported it on the 9th of August. It was seen in satellite images. So this is basically what it looked like on the 9th when it was captured by a satellite image. And, of course, everything is, centric on Manhattan. So, everything is compared to the size of Manhattan. So, yes, it was bigger than Manhattan, to which I can only say nothing is bigger than Manhattan. So, but that's the measure that they had. But this is what it looks like. A couple of things I would like to point out in this, in case you don't see, what you see here is dark, are not holes, but they're cloud shadows. So when the satellite takes this image, what you're seeing there is the shadow of the cloud, from the sunlight, just as a sort of an aside there. But that's basically what the pumice patch looked like on the 13th of August. And it made the news. And there were all kinds of things like, basically it's going to heal the Great Barrier Reef. Some people said it's going to solve global warming because you can see here that there's the pumice patch there, and you can see how just over the pumice patch there are clouds. Now, this is something that Chris and I argue about. It is unclear to me how much coincidental things happen, but in any case, clearly having something like pumice on the sea surface is changing the exchange of heat with the water below. It's just that finding something that is so fine scale as this is, I think, a lot trickier. Trying to prove that it works this way is a lot trickier. But that basically it started breaking up through wind action and it was moving westward. So Tonga was, if you remember, somewhere about here, Fiji is about here, and the pumice raft is moving this way. Then we have a series of images, and this is a coral atoll just north of Fiji with some gaps in between. And you can see how the pumice is approaching it on the 29th of September. And on the 9th of October, you can see along, so if you look at, for example, this bay here, you can see that this would be like those blue beaches that are blue beaches, the beach with the blue waters that we were talking about before. You can see that these are shallow with nice sandy beaches and it's kind of blue. But when you come down to 9th of October, it's all filled in with pumice. So the pumice basically is drifting across and it's landing on these beaches. So that's basically what we see here. Not all the pumice landed on the beaches. There are gaps between the atolls. And so some of it makes it across and continues westward, will sink out at some point or maybe make it to the Great Barrier Reef. We do not know. When it breaks up much smaller than this, we can't see it in satellite imagery anymore. So at this point, on the 9th of October, which is the last image I could find, I thought we were done with the pumice. That was it. So when so this is just a map to show you how this changed over time, and that was the last sighting from satellite images. But then I wasn't sure we'll find it, and then we saw this. And I'll actually say the first pumice piece that I saw when I was looking over the side looked like a little coconut, and I was thinking, there are little coconuts coming off the island. But I threw a net over the side to catch it and see what it was. Saw it as pumice, got excited because if there was one pumice, there's probably more. And sure enough, we were able to find a lot more. We found this using the UAVs. So once we knew there was pumice potentially around, we were able to fly them, search for the pumice, and then take the ship there. So we did not run into this accidentally. We found this because the UAV cameras told us this is where we needed to go. So there were coconuts in the water, incidentally. So just saying. But what does that mean, that you actually see coconuts in the water? The theory is, and there are also some bits of plastic. So the theory is that you saw how the beaches had accumulated with pumice in one of the earlier satellite images that I showed. When you have storms, so that was in 9th of October, we were finding this basically end of November. And the idea is that when there are storms and there's wave action, you slowly wash off those things from the beaches and resuspend them in the water. And then this is basically what we're seeing. So it's completely broken up, but it is essentially coming through. This is what pumice looks like in the satellite, in the drone data. So you can see again, it has a color that we can hunt for, and it has a temperature signal that we can find. And that was the cruise. It was about 40 days long. We've collected 43 terabytes of data. We flew 19,000 kilometers with the drone. 19,000 kilometers is the distance from here to Singapore. So just keep that into account. And that's basically what we were able to fly with the drone in that time frame. They flew for about 240 hours. We flew 44 flights with them over the time that we were there in 33 days with 9 scientists, 3 UAV operators, and 1 ship. And that's basically what it looks like. That was all of us that were on the ship. And absolutely magnificent crew, most helpful. Everybody was super excited about what we were doing. So it was a really successful cruise at the end of it all. And with that, I will say thank you, and I will stop share, and I am ready for questions.
Ajit, thank you very much for another very interesting program.
My pleasure.
And for everybody's information, we're going to try to connect Chris and Ajit so we can get the video recording and edit it, and we'll put it up on the Earth to Class YouTube channel. We also have on the Earth to Class website links to previous programs that Ajit has run. I'll try to make certain we have all the information on there because sometimes it gets lost over the years. I think we have some questions in the chat. I just saw something from Richard. Richard, you want to unmute and ask your question directly?
We don't hear you, Richard, but I will take your question from the chat window while you try and figure out your audio settings. there are different forms of nitrogen. So you have nitrate, that is NO3. You have ammonium. These are the two most common forms of nitrogen. Urea is also there. Urea is less common because it is sucked up immediately. Ammonium is also not so common because, again, it's taken up by whatever bacteria or phytoplankton that exists. Nitrate is the most common form of nitrogen that is available to phytoplankton in the ocean waters. And if you look at it as a profile, you have very little nitrate at the surface because there with sunlight, phytoplankton can take it up. And so there's never any nitrate because whatever is there is used up immediately. But then the concentration increases as you go much deeper where you don't have sunlight, and therefore phytoplankton can't grow because they need the sunlight, and therefore you don't use up nitrogen as much. So you have a profile that's very low, and then it goes up once you get into the darker parts of the water.
Any of the students have questions? We have a lot of high school and college students on with us today, so if any of you have questions, we'll give you priority. Just unmute yourself and ask if you don't want to chat.
And if you don't hear an answer, it's because we don't hear the question.
Okay, I guess we have to open it up to the teachers. Yeah, you see, I'm not the only one who knows about coccolithoporidae.
Mike, there's a question in the chat that hasn't been asked from Sarah Richards. Can satellites show where iron levels are high or low?
Yeah, no, so I was watching that as I was talking, and that's basically what I was explaining, how we can't measure iron directly with satellites, but we can measure dust with satellites, which is a major source of iron, and then we can model how much iron comes out of that. If they're coming out of rivers, we can basically, again, detect river plumes in satellite data, and if that's a source of iron, we'd be able to do that, but it's only indirect mapping. Well, I would suggest, I would encourage you all to go check out that website I put in the chat window. I think there are a series of blogs. So what Alex encouraged us to do, so the blogs are written by various people, but what he encouraged us to do was try and have someone write about something different about the cruise both as a written blog, but then he also compiled a video blog at least once a week. So there are a lot of videos in there that you can sort of look at, including some sort of a summary.
Okay, Ajit, I had a question. How are typhoons affecting the trichodesmium?
How is typhoons?
When a typhoon comes through, how does that affect the trichodesmium?
Right. So, like I said, trichodesmium loves it when it's calm because that's basically where it can grow and outcompete other organisms. And so when you have a typhoon and the water gets completely mixed up, trichodesmium doesn't do particularly well. But there are two reasons why. One is that when the waters get mixed up, then you're able to bring up nutrients that are usually much deeper. So you make nutrients available near the surface, and then other phytoplankton can grow, and they grow faster than trichodesmium, and therefore it loses out. The other aspect of it is that the enzyme that trichodesmium uses to fix nitrogen, called nitrogenase, is poisoned by oxygen. It's a very strange, and this is one of the reasons why it's an enigma. How can it basically do photosynthesis where it's producing oxygen and do nitrogen fixation that you have in nitrogenase at the same time? Because nitrogenase is killed by oxygen. What happens when you have really rapid mixing and a lot of turbulence is that you expose nitrogenase to oxygen. There's a potential exposing nitrogenase to oxygen. So trichodesmium trichodesmium and I share a lot in common. We like warm water and we like calm waters, and we do not like hurricanes and typhoons. Just as a note, trichodesmium blooms are very common in the Gulf of Mexico. And they get disrupted by hurricanes that come through there.
Thank you again very much. Excellent program. Great 200.
Thank you.
So just for everyone's information, we're going to start now on a 2-week schedule because I had so many Lamont scientists who wanted to participate this year. So the next program will be on February 6th. and we're going to have Margie Turin talking to us about Greenland Rising. So I'll send everybody information about it. If you want to join, please send me an email back. Turns out I have a lot of the student emails, particularly those of you from Ms. Mackey. So if you don't hear from me in the next few days, please send me an email to remind me that you're on the program, and I will send you a certificate that you can use for whatever you need it for. Thank you all very much for joining us. We have a nice sunny day outside, a little cold to go kayaking, but you might want to go out for a nice walk.
Hey, Mike, I have one question for Ajit.
Yes.
If we have students who are interested in getting samples of the trichodecium to do some experiments on, would that be possible?
So I guess I can answer that question two different ways. I think one of my colleagues actually has a culture in the lab, and we may be able to get from that. I don't, because of the lockdown, it's unclear how the cultures are being maintained and how rapidly they're growing, and therefore how much excess trichodesmium there is. You know, the thing is that they grow the cultures, and every time it hits the ends the growth phase, they renew the culture and, you know, grow it again. So there's always leftover organisms that would normally get killed and then washed away that can be made available. Those are perfectly viable. They're growing. It is just that you don't want them to grow too much in the flask, so you just keep, you know, renewing the medium. And so there may be material available through that, but I'll have to check with my colleague. Maybe.
I'm thinking about next year's research cycle, because we have students who are doing independent research. So it wouldn't be for this year, but it might be for over the summer or starting next year that they might interest, because we've done some work before with the influence of microplastics on the ability for different types of algae to form slicks and you know, and how they form. So the trichodecium might be something that they normally wouldn't be able to have access to. That might be an interesting question for them to ask.
Absolutely. No, and I would very much encourage that. If I don't know if you have my email, Mike, can you provide Natalie with my email address?
I can do that, no problem.
Okay. If you can please send me an email, what I'll do is I will link you up with Sheehan Haley, who's the lab manager for my colleague Sonia Diamond, and we can sort of plan from there going forward as to what she can make available to you, when, and things like that. The one thing you might want to note is that trichodesmium is a little tricky to maintain in culture. And so but we can talk about that in the sense that the answer is a yes, but there are some nuances that we need to follow up on.
Okay, perfect.
As Ajit said, right now the Lamont campus is mostly locked down. I think we have about 25% of what we had before. But there seems to be some old guy sitting huddled in a chair who keeps popping up around the Lamont campus. I've seen him in the core lab.
Yeah.
Images of him in the core lab and outside guarding the entrance to the campus. So we've had a lot of fun with that image. Okay, everybody. So I hope to see all of you in a couple of weeks for Margie Turin's talk about what's going on with Greenland. In the meantime, thank you all very much and have a wonderful day. Bye all.
Thank you. Bye. Thank you.